So any questions before we continue? So you see, these are our equations. So we define this matrix R such that R11 is equal to cosine theta, R12 is equal to sine theta, R21 is equal to minus sine theta, and R22 is equal to cosine theta. These are how we define the elements of this matrix R. Now let's look at this AX prime. We said that AX prime is AX times cosine theta, but that is AX times R11 plus AY times sine theta, but sine theta is R12. And just keep in mind that what we mean by the X component is the first component, what we mean by the Y component is the second component. So this equation is, in fact, A1 prime is equal to R11A1 plus R12A2. Now let's look at AY prime. AY prime is AX times minus sine theta, but minus sine theta is R21 times AX plus cosine theta is R22 times AY. So this, again, in terms of Y, we can just use 2. Instead of X, we can use 1. A2 prime is equal to R21A1 plus R22A2. Or let's write each one of these equations. A1 prime is equal to R1I times R1J times AJ, sum over J. And the second equation is A2 prime is again sum over J, R2J, AJ. So whatever index we have over here, A2 prime is R2J, A1 prime is R1J. So instead of this 1 or 2, we can just give some arbitrary name. AI prime is equal to sum over J. Now, whatever we have the index over here, I, it is the first index of the R, Ij, Aj. So this equation, this single equation, has the same information as these two equations. And usually we don't put this summation sign. Whenever you see repeated indices, you understand that there is a sum over it. AI prime is equal to Rij, Aj. This is called the Einstein summation convention. Now, whenever you are dealing with many vectors, each vector has an index, and especially if you get some products, etc., you will be summing over indices. The number of summation signs just increases enormously. So just to save some space, we ignore the summation sign, and whenever we see repeated index, we understand that it is summed over. If we see the same index 3 times or 4 times, then we understand that we are writing it wrong. We had made a mistake. Now let's just review the derivatives and integrals in multi-dimensions. Well, most of the time in physics, we are interested in changes in quantities. For example, if you remember the kinematics, when we say there is the velocity, we are actually talking about the change of the position. When we are talking about the acceleration, we are talking about the change in the velocity of an object. And when we are talking about the potential energy, we say that, okay, we cannot measure the potential energy, but we can measure the change in the potential. So for us, most of the time, an important quantity is how something changes. As you just, for example, go from one point to another point, or from one point in time to some other time. And well, in one dimensions, if you just look at the change in the function f, this is usually how we denote it. This we define as, if it is just it depends on one variable only, one argument, we just change it slightly and see how much the function changes. So we have this function f. We are looking at how it changes, how fast it changes at the point x. So to describe it, we just take that point x, shift it slightly, and then we can decide how the function changes, calculate how the function changes. Or in terms of the derivatives, this we can write as df by dx times dx. So the derivative will be the rate of change of a quantity, and if we just multiply it with how much that quantity has changed, we can obtain the total change in a function. This, of course, we can generalize to, this semester we will be dealing with the electric field at every point, or the magnetic field at every point. The potential, we will be defining the potentials at every point. So we will have functions that don't depend on just a single coordinate, but all three coordinates. And then we can ask, how does this function change as we just go to the next point, a nearby point? So we have this point, let's say this is our origin. There is this point whose position vector is r, and we have this function phi, which is defined everywhere, at every point. This is the point r. We just shift it slightly. This is the point r plus dr. So I look at the value of my function at this point, and I look at the value of my function at this point, and I try to see how it changes. This is again nothing but d phi. And well, you should already be familiar with Taylor expansion, also of many variables, right? So this we can write as, for example, if you are using the x, y, and z coordinates, this will be phi of x plus dx, y plus dy, z plus dz, minus phi of x, y, and z. I can just make the Taylor expansion of this first term, dx, dy, and dz. They are very small because I'm considering 2 points that are very close to each other. So this will be phi of x, y, and z plus the derivative of phi with respect to x times the change in x plus the derivative of phi with respect to y times the change in y plus the derivative with respect to z times the change in z minus the value at x, y, and z. You see, each one of these terms appearing over here is just like the term over there, but since I can change x, y, and z, my function will change both due to the change in x, the change in y, and the change in z. All those changes will cause changes in the value of my function, so I'm just adding them up. And what I am left with is d phi by dx plus d phi by dy times the change in y plus d phi by dz times the change in z. So if I just shift my point very slightly, this is how much my function will change. This is, in a sense, the generalization of the equation on the first line to three parameters, 3 arguments. Well, if you look at that first line again, well, we have a function of one variable. Here we have the derivative with respect to that variable. This line over here also, well, this is the generalization to three variables, but we can just combine them. Let's just write it in this form. Because if you remember the definition of the scalar product, what the scalar product does is just multiply the corresponding components, the derivative with respect to x times dx, the derivative with respect to y times dy, derivative with respect to z times dz. That is dz in the z hat. And, well, these two lines are equal. But this is nothing but the shift in my position. So you see this dr has components dx, dy, and dz. That is how I define the dx, dy, and dz. When I add this dr to my vector, the components change by dx, dy, and dz. So this vector over here is nothing but dr, the change in my position. So this d phi, the change in my function, is nothing but, well, this weird-looking expression, which we will call gradient of phi dot dr. And here, the gradient of phi is just this, the vector obtained by taking the derivatives of my function phi with respect to its arguments. This is called the gradient of phi. Now, in fact, here the derivation that we had done was based on the fact that we are using Cartesian coordinates. Now, later on, we will be discussing different coordinates, like the spherical coordinates, the cylindrical coordinates, or you can just invent your own coordinates. And in these new coordinates, if you want to obtain the expression of the gradient of phi, this is the definition that you should use. This you can treat as the definition of gradient of phi. If you start from here and express dr in terms of x, y, and z coordinates, then dr is just dx in the x hat, dy in the y hat, dz in the z hat, then you would see that this definition is equal to that one over here. Well, just let's see how we can see it in Cartesian coordinates. So let's just choose, for example, well, this change in the coordinates is just arbitrary. I can choose whichever one I like, and this equality should be satisfied whatever dr is, as long as it's very small. Its magnitude should be very small. Well, if dy and dz are 0, then d phi, which in this case is nothing but phi of x plus dx, y and z, minus phi of x, y, and z. Since dy and dz are 0, the y and the z coordinates I do not change. So the definition, the change in phi is only due to the change in x. And this should be equal to gradient of phi times dx in the x hat. But this is nothing but dx times the x component of gradient of phi. Because if I take a vector and take its scalar product with x hat, it just gives me the x component of that vector. So the only thing left is just divide both sides by dx. So gradient of phi, the x component, should be equal to phi of x plus dx, y and z, minus phi of x, y and z, divided by dx. But this is nothing but the definition of the partial derivative with respect to x. So basically, although we had derived this expression, or we had defined this expression in the special case of Cartesian coordinate system, where we chose the coordinate axes x, y, and z, this is more general. This is valid in every coordinate system that you choose. I mean, they don't have to be orthogonal, they don't have to be straight, etc. Whatever coordinate system you choose, as long as you are able to express your dr in that coordinate system, you can express your gradient in that coordinate system. Now let's look at this one again. Gradient of phi, this is equal to, let me just write it in this form, x hat del phi by del x plus y hat del phi by del y plus z hat del phi by del z. Well, let me just change it slightly. X hat del over del x plus y hat del over del y plus z hat del over del z, acting on phi. But this kind of looks like we have a vector multiplying a number, a scalar function. So we have this operator which has its components. Well, in this case, the components are not vectors themselves, they are just taking derivatives, multiplied by some number, some scalar function. And this operator over here, we denote it by this inverted triangle. So this is the, basically that notation over here comes from this definition. This thing over here as a whole is what we call this gradient operator. And what we should understand from this expression is, well, nothing if you just see this expression, but when you multiply it with a function, phi, a scalar function, you should expand it, you should just take the derivative, you will get a vector whose components are the derivatives of this function. So that is what this operator does. If you just give it a function, it gives you a vector. And the components of this vector that you obtain are nothing but the derivatives of your function with respect to x, y, and z. Of course, this is true only in Cartesian coordinates if you choose your coordinate axis x, y, and z. If you choose spherical coordinates or cylindrical coordinates, it will look different. But it is in x, y, z coordinates, this is its form. Now let's try to understand what it does, the gradient of phi. Well, this is the definition that we used. What is this? How do you calculate the scalar product of two vectors? Magnitude of the first one. The magnitude of the second one. Cosine of the angle between the two. Now let's just imagine that we fix dr to some constant value, very small constant value. But we just change its direction. The magnitude is fixed, but we are changing the direction. Okay? So what is the maximum possible value of cosine? 1. When theta is equal to 0, cosine is 1. So this number over here is maximum when theta is equal to 0. That is when dr and gradient of phi, they are in the same direction. Now, gradient of phi is determined by phi. So there's no, once you choose your function phi, once you are given that function, you don't have any freedom over here, but you are free to choose this vector dr. And whatever vector you choose, the change in phi when you take one step in that vector, in that direction, will be given by this expression. And the maximum possible value is when dr is in the same direction as the gradient of phi. So just imagine this one. You are in a hill. You are taking just one step, which will be 10 centimeters long. Well, if I take 10 centimeters long here, nothing changes, almost no change. 10 centimeters here, no change. 10 centimeters here, no change. 10 centimeters over there, there's a large change. The maximum change will be in this direction. So that is, the change is this one. That change is maximum when I take a step in this direction, but that basically means that gradient of phi is in that direction, in the direction in which phi changes fastest. No? Yes? Yes, no, not convinced. Okay, so give me your jacket. So here we have a jacket of some arbitrary shape. Just imagine this phi is the height of this jacket. So how do you specify a surface in 3 dimensions? So for a given x and y, you have to specify how high that surface is. Okay, so in this particular example, (3D) surface. If you just tell me that the z coordinate of that surface is a function of the x and y coordinates, then I know the surface. Then I can talk about this gradient of f. Of course, I can only talk about this gradient of f at a given point. Not at everywhere, but at a given point. Now, not an arbitrary, at a given arbitrary point, if you tell me the x and the y coordinates, I can calculate this number, I can calculate this number, so I can talk about this vector at that point. At every point, the gradient will be pointing in different direction. Okay? So let's look at this one, this jacket. Let me just pick up this point over here, let's say. Okay? Now, if I start from this point, I can move in that direction. Okay? If I move in that direction, then f is decreasing, right? So df is df. Now, one thing I know is whatever direction I choose, if I just take a very small step in that direction, a very small one, the change in my function f, in this case the height from the surface, will be given by gradient of f dot dr, which you had said that this is the gradient of f, its magnitude, times the magnitude of dr times cosine of theta. Now, I started from this point, and if I move in that direction, then f is decreasing. F is decreasing means df is negative. Df is negative means, well, these numbers are positive. Then cosine theta is negative. Well, that basically tells me that this vector dr, remember theta is the angle between dr and gradient of f. If cosine theta is negative, that is theta is larger than 90 degrees, if we take the small angle, it should be something between 0 and 180, but I also know that this is negative, so it should be somewhere between 90 and 180. So if gradient of f is pointing in this direction, this is my dr. Remember, I'm moving in this direction. So this is my dr. So the gradient of f is somewhere in that direction. I don't really know where, but somewhere over here. Okay? Now let's look at this direction. Now in this direction, the height of this surface is not really changing. Well, if the height is not changing in that direction, the f is 0. Well, gradient of f, I didn't change the gradient of f. This is given by the surface itself. But the only thing I'm changing is dr. I'm just taking dr to be pointing in different directions. So in this direction, I change dr. Its magnitude is non-zero. This is not 0. This is not 0. That means this should be 0. So I know that if dr is in that direction, then gradient f is somewhere over here. It's 90 degrees, sorry, not somewhere over there. It's somewhere in this direction. So because this was my dr, I know that gradient of f is perpendicular to that one. Let's go in that direction. I'm going uphill. Well, if I'm going uphill, I know that df is positive. If df is positive, I know that I'm keeping this one constant. This I'm not changing at all. It just tells me that cosine is positive. Well, if cosine is positive, it just means that it's somewhere between 0 and 90 degrees. So I chose my dr to be pointing in that direction. If I choose dr to be in that direction, then I know that gradient of f is also pointing somewhere in that direction. Because I already know I'm going uphill, df is positive. If df is positive, that just means that cosine theta is positive. So if cosine theta is positive, it's telling me that theta is somewhere close to 0, let's say, between 0 and 90 degrees. Well, if this is my direction of dr that I chose, then gradient of f should be in this direction, somewhere there. Now, for the maximum df, I can only obtain the maximum df positive number when dr and gradient of f are exactly in the same direction, when theta is exactly 0. Well, when theta is exactly 0, df will be maximum. Since I'm looking at this point over here, df is maximum if I take a step in that direction. If I take a step, that is when df is maximum. But that tells me that gradient is also in that direction. Because in that direction, cosine theta will have its maximum value, it will be 1, so that df will be maximum. But that tells me that gradient of f is actually in the direction in which my function increases the fastest. So if you just want to find the direction in which your function increases the fastest, the only thing you have to do is just calculate the gradient. It already gives you the direction in which your function increases. Thank you. Any questions? Okay, I will just review it shortly in Turkish, if you don't mind. Şimdi bakalım, df dediğimiz şey neydi? Fonksiyonun çok az bir yer değiştirmesi, yani konumunu çok az değiştirdiğin zaman fonksiyonun ne kadar değişiyor? Tamam. Şimdi şunu şöyle düşünelim, biz bir noktadan başlıyorduk, noktayı diğer kadar kaydırıyoruz. Bir adım attığımızı düşün o doğrultuda. Adımımızın büyüklüğü sabit olsun. Herhangi bir yönde adım atabiliriz ama sabit büyüklükte olacak. Şimdi adımın bu sabit. Bu zaten benim bulunduğum nokta ve işte fonksiyonum tarafından belirlenen bir şey. Bu da sabit. Adımın yönünü değiştirdiğim zaman değiştirebileceğim tek şey bu. Ben öyle bir yön seçebilirim ki bu df maksimum olsun. Alabileceği maksimum değişiklik. Fonksiyonumun sahip olabileceği maksimum değişiklik. O yönü nasıl belirlerim? diyarı öyle seçmem lazım ki teta 0 olsun. Ben eğer diyarı öyle teta 0 olacak şekilde seçmek istiyorsam şayet yapmam gereken şey diyarla gradient f'i aynı yönde seçmem lazım. Diyarı gradient f ile aynı yönde seçersem o zaman fonksiyonum en fazla değişecektir. Adım uzunluğum sabitse. Bir başka deyişle birim adım başına fonksiyonumun en fazla değişeceği doğrultu gradient f doğrultusu. So if you are going uphill, for example, if you calculate the gradient of the function of the hill, and then if you take that direction, then you will be reaching the top the fastest. Okay, so we have this gradient operator here. Well, it is a vector, and the gradient of a function is just like a vector multiplying a function, scalar function. But if we have a vector, we can multiply it with another vector if you want. And in fact, there are two possible ways of multiplying them. We can talk about the gradient of, or the divergence of a function a, which in Cartesian coordinates, we define it as you take the well, I mean, just keep in mind the definition of the scalar product in terms of the components. Scalar product ax plus ay plus az. This will be equal to, well, the scalar product of two vectors in terms of its components is just multiply the corresponding components. I multiply del by del x by ax, and del by del y by ay, and del by del z by az, and sum them up. This is how we define the divergence of a vector field. Now, of course, if you don't use the x, y, z components, but we will be seeing the spherical coordinates, for example, then you have to be a bit careful, because if you take the derivative with respect to x, we said that x hat is just a constant vector. So its derivative is just 0. We don't need to pay attention to the derivative of x hat. But we will see in other coordinate systems that these unit vectors also change from point to point. In such a case, you have to pay attention to how those unit vectors also change. Now, we will study it in more detail on Friday, but I mean, just keep in mind that here we are using the fact that x hat is their derivatives of x hat, y hat, and z hat, they're all 0. And before you go for today, let me just define what we mean by the curl of a function, and on Friday we will discuss it in more detail. What does a curl mean? What does the divergence mean? The curl of a vector field, again, just use the conventional definition of the cross product. This is del by del x in the x hat direction, del by del y in the y hat, and del by del z in the z hat direction, cross product with ax in the x hat plus ay in the y hat plus az in the z hat. Or you can write it in this form, x hat, y hat, z hat, del by del x, del by del y, del by del z, ax, ay, az. This is equal to, in the x hat direction, derivative of az with respect to y minus the derivative of ay with respect to z. minus in the y-hat direction. Just close this column and this row. We have these two and these two. And the determinant of this 2 by 2 matrix is derivative with respect to x of az minus derivative with respect to z of ax, and plus in the z-hat direction, again, close the first row and this last column. So we have these 2 by 2 matrix over here. Just take its determinant, derivative of ay with respect to x minus derivative of ax with respect to y. Or if you like, you can straight away write the ith component of this one. This will be epsilon I j k, derivative of ak with respect to xj. All of them are the same thing. I mean, this operator over here, well, this is the curl of A. This operator just likes as ordinary vector in these operations. Of course, you have to pay attention to the order of how you put the things. I mean, you cannot just put ay times del by del x. It is del by del x of ay. With that in mind, you can just treat it as an ordinary vector, well, as long as you are using Cartesian coordinates at least. In spherical or cylindrical coordinates, I mean, you will not be able to do that, but in Cartesian coordinates, you can just treat it as an ordinary vector. Just keeping in mind the order of things. You see, in this expression, in that expression over here, you first have the derivative, then the components of your vector, and in the final expression, then you have the derivatives of the components of the expression of your vector. Any last-minute questions? So see you on, tomorrow we don't have a recitation. There's nothing much we had done to do a recitation. And we will meet on Friday.